Got it? All right. I'll begin. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students for another week. Successfully completed, I think. And I just pray to be with us today. Help us again, Lord, to glorify you in what we do, Lord. In your name I pray. Amen. Okay, so this is, by my count, lecture 6. Let's see here. And I will continue to talk about groups. And hopefully we'll get to subgroups today. So I'll lead with an interesting, it's not exactly an example as much as it's a whole class of examples. So example 1, a nice example of a group. And in fact, this is, it's kind of well, first of all, what was a group? We learned last time a group is a, what is it? It's a monoid in which every element has an inverse, right? In other words, it's a set with an operation which closes on itself. Every element has an inverse. There's an identity element. And then what's the other pesky thing we need for the operation for it to be a group? Associativity, which is trivial, right, until it's not, right? Yeah, you experienced that firsthand. So I think my mission is accomplished with that homework problem. So GLNR, what this is, well, this is actually MN, R star, or in my usual notation, R n by n star. It's the group of units of n by n matrices with entries from R. And here R could be rationals, reals, complex, integers, even Z mod n. I mean, there's more than this you could do, but certainly this is a good list of examples. That little Zn at the end, that's not one example, right? That's like countably many examples. So this is a lot of examples. And by the way, this can also be done, I really shouldn't conflate this n and that n. So let me say Z sub m for just this, for the moment being, because there's no connection between this and that, all right? So a more perhaps useful description of this is it's just A in Rn by n such that what? Such that the determinant of A is, now you might be tempted to say not equal to 0, but that would be wrong. You should say the determinant is an element of the group of units of R. Now the reason for this is that the classical formula for the inverse that you learn in linear algebra is the following. You say inverse, it's equal to 1 over the determinant of A, all right, the adjoint of A transpose, I believe. Everybody memorizes the 2 by 2 version of this formula, but this is equally good for n by n matrices. This is a straight up formula for the inverse. And okay, so this needs to be interpreted as determinant of A inverse, the adjoint of A transpose. I mean, for example, if you look at A, B, C, D, it's equal to AD minus BC inverse, then the transpose of the adjoint is you flip the diagonals and you put minuses on the off diagonal. That's how the 2 by 2 goes. All right? The point is, the proof that that actually serves as the inverse matrix, what does it involve? Basically just the product of just that you multiply entries in the usual way, that you've got addition and multiplication in the usual way defined, right? That there's this multiplicative inverse that determinant of A over determinant of A is 1. So if you think about all the steps that go into showing that this formula for the inverse is an inverse for a field, they equally well apply in the cases like Z mod M, or Z, which are of course not fields, in the sense that they have many elements that are non-zero and yet are not units. you know, Q, R, and so let me get to it here. So like R star, what is it? Well, Q star is just what? These are all kind of the same story. Just take out 0, right? But that's because these are fields. Everything non-zero is a unit. In contrast, Z star, as we talked about last time, 1 minus 1, and Zm star, well, that's K in Zm such that the greatest common divisor of K and M is equal to 1, right? Relatively prime residues to the modulus. So, for example, here's an element 1, 0, 0, 0, 1, 0, 0, 0, 1 would be an element of GL3Z. Because, well, of course you know this is the identity matrix, right? So the determinant of the identity matrix is 1, right? Little linear algebra refresher for you. Not really linear algebra, honestly, matrix theory refresher for you. What can I do to that matrix and stay in GL3Z? Yeah, I can flip rows, I can flip columns. What else can I do? So you said flip rows, I'll do that. How about this? I can do this. What did I just do? I added row 1 to row 2. Row additions don't change the determinant. So I can add rows all day long, you know. Scalar multiply, I don't know about that. If I multiply by 2, I'm in trouble, right? Because we have this pesky formula. The determinant of C times A is, in this case, this context, C cubed, determinant of A, right? So you say scalar multiply, I say sure if you're talking about plus or minus 1. So, well, okay. Yeah.
Scalar multiply in Z star.
Yeah, so how big is GL3? Like what's the size of GL3Z? I mean, Z star may only have 2 things in it, but GL3Z, it looks to me like it's got a lot of things, doesn't it?
Keep adding rows forever.
Yeah, I mean, it's going to be countably infinite. On the other hand, if we were to look at GL2 Z2, well, that's going to be finite. Because here you're looking at, you know, A, B, C, D. In Z2, 2 by 2, such that AD minus BC is equal to what? There's only one unit in Z2. What is it?
1.
1, right. How many matrices are there in, how big is this? How many matrices in here?
16.
16, right? So this is at most, well, it's not. It's definitely not order 16, right? It's going to be smaller than order 16. What is it exactly? I don't know. That seems like a homework problem. So, not that it actually is. I'm just saying it could be. So, I think this is a great class of examples. We'll come back to this, of course. All right? So, matrix groups are important and interesting. It's understood that the group operation here is matrix multiplication, right? We can also, of course, look at, I mean, if you want, this is, I mean, I hadn't planned on this example, but I guess it's kind of warranted to say this. If you just take R, n by n, with addition, right? For R equal to what? Q, R, C, Z, or Z mod M, that's also an additive. That's an additive group, right? With respect to matrix addition. Multiplicative group with respect to matrix multiplication. The identity in here would be the 0 matrix. The identity in there is the identity matrix. Okay? Great. So our next sort of family concept I want to try to get at, I'm trying to illustrate in the next few examples, is the concept of generators and relations. In other words, that we can describe the structure of a group by stating it in terms of generators and relations. Wait a few minutes. Yeah, sure enough. Okay, so never mind. I'm not talking to myself this time. Let's see here. Example 3. So here's a good example of generators and relations. We could talk about D3. Oh, let's not do D3. I'm sorry, that's not what I want to start with. Un momento. I'll get to it eventually. Come on. This is what he calls K4, the so-called Klein 4 group. And what it is it's generated by A, B, and C, all right, such that A squared equals to B squared equals to C squared equals to 1. AB, sorry, this is, I usually try to list them horizontally, but I'm just, a question of board space, I'm going to have to list them vertically, okay? Hope that's okay. AB, I'm going to do it. AB equals to C. If you do it, I'll take off points. BC equals to A. Sorry. AC equals to B. And while I don't want to list them explicitly, commutative. So, I guess to be utterly pedantic, what would commutative mean? It would mean all possible products commute, right? So like AB equals BA, AC equals CA, BC equals CB, and I write 1 there. 1 is understood to be the identity. So it turns out that we can argue that K4 has got 4 things in it. It's got 1, it's got A, it's got B, it's got C. These relations I've written over here suffice to describe the rest of the multiplication table for the Klein 4 group. I'm already regretting this as a leading example for generators and relations, but it's too late. I'm already this far in. So you'll just have to hang with me here. We'll get a better example next, but we'll start with this one. Now, so if we can fill out the Cayley table, then we've defined the group multiplication, right? And my claim is that saying that there's A, B, there's C, and this is how you multiply them, suffices to generate this group. Of course, we could, all right, getting to it. So the first row and the first column are automatic from the assumption that 1 is the identity. And we are assuming that. Okay? Then what do I have? From the generators and relations, I'm given that A times A is 1, B times B is 1, C times C is 1, right? AB is C. I'm sorry, this is kind of a dumb example of generators and relations because I've pretty much written every single stupid thing in the Cayley table as the form of a relation. So this is not really what I was trying to, it's an example of generators and relations, but it's kind of a dumb example. But hey, you've been listening to me long enough, you know that that's not surprising. Let's see here, so C times A is B, C times B is A, so. Now, if you look at this, you can see that it has the nice properties we want for a Cayley table, right? Every element of the group just once in each row and column. That's a good sign. Let me see if I can come up with a better example. I have better examples here. I just got out of order. I guess I got to go back. Yeah, fine. I had planned for this stupid S3 example at the start of class, so I guess I got to go back to that, kicking and screaming. I didn't want to do it. It's going to take me 10 minutes. Example 4. Tell you what, I'll try to speed it up. So suppose you've got G, which is generated by sigma and tau, such that sigma cubed is the identity, and tau squared is the identity, and we also have that sigma, tau, sigma is equal to tau. I mean, the generators and relations here didn't really illustrate the efficiency of the notation. By the way, that's bad, 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 bad. So sorry. This is more it. So here, these are the generators, pipe, relations. The claim is that this is a presentation of the group, and if we work out the consequences of this, we can actually argue, and I'll show you this, that G is in fact equal to, come on, where'd you go? E sigma, sigma squared, tau, tau sigma, and tau sigma squared. All right? And so let's work on filling out the Cayley table for this thing. Now, this is a better example because, as you can see, I haven't actually told you every single possible product in the relations, right? So maybe you can appreciate the idea of generators and relations better from this example. Now, some of this is really easy, right? So let's get the easy part out of the way. First row, first column. It's actually important to write this because it's going to be useful to have this written for the purposes of a process of elimination as we work out the products here. See, because we can always use as a guide for our calculations the fact that every row and column should have what? Just one element each. Now, I should be careful not to include the label row and the label column in that analysis, right? They don't count. These are just, so like, I got to look inside the red line. Yeah, okay. Okay, so what's given to me? Sigma cubed is what? E. What else do we have? Tau squared. Tau times tau is E. What else do we know? That's it at the moment, right? Is that in, is there anywhere sigma, tau, sigma here? Yeah. Ah, you guys are smarter than me. Thank you. I mean, anyway, you can see that. So that's what this. So your point is that this is tau. That's also given. Is there anything else, though? I mean, that's it.
Tau sigma squared.
Tau sigma, where is that in the relate? That's not a.
Third row, third row.
But how does
Fourth
that?
row, third column.
Tau sigma squared. What do you mean, tau? Yeah, but that's not directly here is my point.
No, it is.
It is not.
Fourth row, third column.
But tau sigma squared, tau.
Tau by sigma squared, tau sigma squared.
I'm sorry. So which one again?
Fourth row, third column.
1, 2, 3, 4. Third.
No, third column. Yeah.
Tau sigma squared. That's up here?
No,
It just
it's
goes.
in G. It's an element of G.
Well, yeah, I know that, but is that here?
Are we not trying to just fill in the table?
We are, but my point was these are from the relations directly. Now you're thinking, which is good. I just wasn't there yet. So, I'm not disagreeing we can calculate. In fact, that's the whole point. Is like, you're totally right. So
That's the point, is that one that doesn't require, that's one that doesn't require a calculation.
how does this not require calculation?
Because it's in.
Oh, I'm an idiot. You got me. I'm sorry. Yeah, you're right. You're right. You're right. I'm sorry. I'll get with you. I tried to repeat to myself 10 times before class that I will not argue with you during class, but I'm still coming to terms with this reality. So you're right, though. Tau sigma squared is there. And what else do we have?
There's the other sigma, tau sigma.
And also tau sigma here, right?
Sigma squared up there.
Sigma squared. Oh, yeah, sigma squared is just sigma squared. Is there anything else that's just by labeling or relations?
Sigma gives sigma squared.
Say again?
Fifth row, second column.
Fifth, second column here.
Yeah.
Oh, tau. Oh, thank you. Tau sigma squared. Anything else just labeling?
Probably.
Probably. Here's the sigma tau, right? Oh, but we don't have sigma tau, do we? Okay.
Can you do anything with the two sigma squares? Does that make sigma cubed times sigma?
Yeah, let's get into it. So sigma, sorry, I'm making this artificial divide into the calculation between what's basic and what's derived. That's just silly though. Oh, you okay? Yeah. Not yet. You have to hold it. Sorry, buddy. Sigma squared is, like you just told me, sigma cubed sigma, aka sigma. So that does this one, right? How about sigma tau? How about tau sigma squared? Which would be this guy, right? Yeah, because that's tau sigma cubed, also known as tau. Aha! Well, because we did the calculation this way, we get one for free. Sigma squared e sigma tau sigma. What's this got to be?
Tau sigma.
It's got to be tau sigma. And so that tells us that, I mean, that's assuming things, I suppose. You could present, I mean, I guess in principle you could have generators and relations that don't form a group, but my point is you could also derive this from the relations. So we have is tau sigma squared times sigma squared is what? Tau sigma cubed, which of course is, as we've figured out, tau sigma. All right. And the story goes on. I mean, we can prove the following, the rest of the table. See here. Where have I got here? Under tau. Tau sigma squared, tau sigma, e sigma squared, sigma, under the tau sigma, we've got tau sigma squared, sigma, e, and sigma squared. So we can complete the last column by process of elimination. What is it? Tau sigma? Oh. No, there's no mistake. Sigma, I refuse. There can't be. Is there one?
Fourth column,
Dang it.
the two in black, two in
Yeah, how do you get those?
The top, which one?
green. Oh, is it because it's not commutative?
What do you mean? Which one is in doubt?
The two green ones right there that you're pointing to.
Oh,
These ones?
Can you just explain how you got those?
yeah.
I copied them from my notes. You offer me. Okay, so this one, what am I missing here? Tau. And this one, sigma squared. This one, sigma. This, oh, I don't know. This one, e, yeah. And then this one then must be tau. You can derive the other ones that I just wrote down by arguments similar based on generators and relations. For example, the fact that sigma tau is equal to, what was it, tau sigma squared? Is that right? That's one of my claims that I haven't justified yet, right? How do you derive this? Well, sigma, let's say, start with tau sigma squared. This is,
Because sigma cubed equals e means that sigma squared equals sigma inverse. And
Yeah.
then we use sigma tau sigma.
yeah, it's messing with my head. In my notes, I've got it written like right to left. So my notes, I started, but let me start with sigma tau. For some reason, it's easier. Sigma tau is sigma tau e, which is sigma tau sigma inverse, which is sigma tau sigma inverse, which is, what's sigma tau? tau sigma inverse, which is tau sigma squared, which is what Sam said like 30 seconds ago. But yeah. All right, enough. This is generators and relations. Yeah.
How do we know that those things are the group? Like just from the...
Ah, yes. Good question. So this does not prove associativity. And I mean, it's an open, there's something left to prove in terms of absolutely being sure it's a group. Certainly, you can see from the Cayley table that everything has an inverse, right? You can see that it's closed, right? You can see that there's an identity, it's E. So what's left to prove it's a group?
Well, it's just associativity.
Associativity, which is tough.
More than that, though, how do we know that the group is E sigma squared, like on the second line there? How do we...
That's because of these calculations. It's not manifestly clear just looking at this that that's all that's there.
So you'd have to go through this whole process.
This comes from performing these multiplications.
From the table.
Yes. Good question. So, check this out. If I look at, let's say, G prime equal to, say, A comma B, such that, yes, Isaac?
Now can I go in?
No, still not yet. Sorry, buddy. I know. Well, that's why we went before class. Let's see here. A equals to 1, 2. We went to the secret bathroom. Well, I shouldn't tell you about that. It's a secret. A equals 1, 2, 3, and B equals to 1, 2. Right? I'm saying that these are, as in 1, 2, 3, and 1, 2 elements of S3, okay? You can show that, in fact, A cubed is epsilon. You can show that B squared is epsilon. And it's a relatively simple matter to prove that A is equal to B again. You can check it. Oh, wait, I got that backwards? No, I don't. So like 1, 2, 3, 1, 2, 1, 2, 3 is equal to 1, 2 again. I invite you guys to, you can check that. It's easy. Right? So these permutations, 1, 2, 3, and 1, 2, satisfy the same relations. Right? Satisfy the same relations as this abstract group I proposed in example 4. So here's example 4 prime. Okay. So my point to you is the same math happens, the same pattern fills out for S3. Well, I mean, that's my argument. I mean, that's my point, is that G prime also will be the set E, well, we're using, sorry, epsilon, A squared, B, BA squared, right? And this, of course, is a subset of S3, but S3 has 6 things in it, so it is S3. What does that mean? I don't know what homomorphism means yet, but what I'm trying to say is, if we draw the Cayley table, right, for this, it's the same as that, right? But on the other hand, it's also a Cayley table for what? For S3. We already know S3 is associative, so it has the same pattern, which we could use to argue that this must also be an associative operation. That's a slightly informal idea. It's just based on like the same pattern. Okay? Here, let me show you another example of generators and relations, which is important. And it's a nice example to have sitting around. I won't spend too long on this example. I mean, we'll come back to it. It's probably as important as CN was last time. It's like a go-to, nice, easy to manipulate example. It's called the Dihedral Group. So example 6, we can say dn, it is generated by x and y such that x to the n is 1, y squared is 1, and one final relation. Come on, where'd you go? Still not hardwired in my brain just yet. Xyx is equal to y. All right. At the moment, I'll leave it as an exercise for you guys, but you can show that dn actually looks like 1x, x squared, dot, 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 x to the n. Oh, x to the n minus 1. We already got that one here, right? And then y, yx, yx squared, dot, 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 y to the x n minus 1. Fundamental identities you could prove. Here's a hint on how to calculate with this. Show that if you have x to the n times y, that's equal to y times x to the minus n for any n. Oops. With that identity in hand, it's pretty easy to show that these all square to 1. In other words, these guys are all elements of order 2. Okay. It's another nice example of generators and relations. We'll come back to this one later. Again, the Dihedral group. Okay.
Is example 5 secret?
I'm sorry?
Do you have example 5?
What happened? Did I skip 5? Was it go straight to example 6? Yeah. Fine. Example 5. D3 would be 1x, x squared, y, yx, yx squared. There you go. That one's free. Okay. Where'd my eraser go? Oh, here it is. So an important thing we need for constructing new examples is the direct product of groups. So let's say if G sub I, comma, star sub I is group for I equals to 1 to dot, 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 n, then define star on G1 cross G2 cross dot, 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 cross Gn. Oh, unfortunate. Let me call this G. And we'll define star on G cross G to G. Yeah, I don't want to write that again. Bye. So here's it goes. If we have x1, x2, dot, 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 xn, and we want to multiply that by y1, y2, dot, 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 yn. So let's say for x and y and g. So this is x, this is y. X times y, how do we define it? x1, star 1, y1, x2, star 2, y2, xn, star n, yn. All right, this is the direct product of groups. We do the operation of each group and each component. They could be different operations. You could have addition in one and multiplication in the other. You could have a direct product of the three things. You could have addition in the first, multiplication in the second, and composition of functions in the third. All things are possible. Okay. So the theorem, super nice, is that G, comma star, as above, is a group, and 1 in G is exactly the tuple of the 1, well, let's say E1, E2, dot, dot, dot. I guess I should say EG here because otherwise it just seems awkward, EN, where EI is identity in GI. Also, the inverse, if I have, G1, G2, Gn, I calculate the inverse of it, well, it's the tuple of inverses, so it's G1 inverse, G2 inverse, Gn inverse. The proof of this is pretty easy. It makes a great test question. Not in the book, easy to work through. I'd encourage you to do it. Yep.
Sorry. Is your star in both cases the same? Because you're writing star in one place for, like, on top, like, two different shapes, basically. Well, it is the same.
The one is in GI and the other is in G.
I have 5-pointed stars on the components of the group, but I have a asterisk star for the group itself.
So they're different.
Yeah. I mean, I'm defining star, the asterisk, using star 1, star 2, star n. In Nicholson, he just used juxtaposition for everything, and he doesn't distinguish between the identities. He just uses a 1, 1, 1, 1, 1, 1, and you're just expected to know that it's the appropriate one for the appropriate one. Which makes sense, but, I thought I should clutter things a bit to be more descriptive in here, yeah. You'll forgive me if I don't prove it, because it's not especially interesting. If you ask me in the help session, I'll do it, but anyway, so this is the direct product of groups. An important direct product to look at would be, here's one. Z2 cross Z2, under addition, of course. So I have 0, 0, 0, 1, sorry, I'll get with it eventually here, 1, 0, and 1, 1. Hope I chose the right order. Let's see here. I mean, there's no wrong order, but pedagogically, there's a preferred order for the point I'm making after this example. What example am I on? 7. So you guys you add mod 2 each component, right? This is not that tricky, right? You got 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0. I'm doing it column by column. Don't look at the board, just do it yourself, right? It's faster, way faster. Let's see here. Oops. Now, if I did it right, what should we see? No repeats, right? And did I win? Okay, let's see here. 0, 1. Okay. Think we're good. Yeah, okay. So this is the group G, let's say, is equal to Z2 cross Z2, all right? Okay. Example 8. This one's even more heavy-handed. Let's look at the Cayley table for Z2, and I'll put bars in for my reasons. Sorry, Isaac, gotta wait, buddy. And how about Z star? Cayley table for Z star. I mean, this example is in Nicholson, but it's worth repeating for sure. I'm going to add something to what he says, though. So, I mean, technically, these are different sets, right? I mean, this is a set of residues, mod 2, even numbers, odd numbers, how to multiply them. I mean, excuse me, how to add them, right, as classes. This is a multiplicative subgroup of the integers. These are different sets. And yet, you can look at these two tables, right? And you can see that really that's the same, it's in some sense the same group, right? It's the same structure, it's the same pattern. We could argue that as groups, these are the same thing. It's just, in some sense, this is just a different notation for the same thing, right? It's What's the notation change? 0 bar is being changed to what? 1? And what's 1 bar being changed to? -1, right? We could even define a mapping. We could say psi of x bar is equal to -1 to the x. You can check that that mapping is well defined, even though I used a representative of the coset to define it, right? If I choose a different odd number, if I choose a different even number, -1 to that is still either plus or -1. And you can check. The following is also true. Psi of x bar plus y bar, guess what? It's equal to psi of x bar times psi of y bar. So this psi, it's a mapping from Z2 to Z star. In fact, it's a bijection from Z2 to Z star that takes the group operation in Z2 and transfers it to the group operation in Z star. Psi is what we call an isomorphism. Okay? And we say that Z2 and Z star are isomorphic as groups. To say two groups are isomorphic basically means they have the same structure, it's just a change in notation. The notation changing map we call the isomorphism. Again, technically an isomorphism is a bijection which preserves the group structure. Isomorphism.
So is this slightly different from the definition of isomorphism in linear algebra?
Yes, in linear algebra we have more to work with. We have to preserve linearity. There's no addition here and scalar multiplication, right? There's just the group operation to preserve. So over here, in fact, the Klein 4 group and Z2 cross Z2 are also isomorphic. What's the change of notation here? I mean, notice that every element has order 2, right? 0, 1 plus 0, 1, 0. 1, 0 plus 1, 0, 0, right? The sum of any one of these in itself is 0 again, right? These all have order 2, just like A, B, and C all have order 2, right? And how about this? A times B, what's A times B? A times B is C. So I suggest that this is really A, this is really B, and this is really C in disguise. And I propose that we could show that psi, if we say psi of 0, 1 equals to A, and if we say that psi of 1, 0 equals to B, and if we say that psi of 1, 1 equals to C, we'll be able to prove that this will generate an isomorphism from the direct product of Z2 and Z2 in the Klein 4 group. Now, you don't actually have to do that. To prove two groups are isomorphic for low order, it suffices to look at two Cayley tables and say, aha, it's the same pattern. If you can say these two Cayley tables have the same pattern and you can give me the dictionary, right? A lot of times we wouldn't even write psi. We'd just say something like 0, 1 maps to A. This you'll see in books a lot. They won't even give a name to the isomorphism. They'll just show you the correspondence. But if you can do that, if you can find the correspondence and you can show that the two Cayley tables have the same pattern, that suffices to prove those two groups are, in fact, what is called isomorphic. Yeah?
Can you make the same argument from like the generators and relations, even if you don't, like say it's like a bigger thing that you don't really feel like writing out a huge Cayley table for? Like if you have two groups that are generated
So
with the same structure.
you're basically starting to ask the question, how do we tell when two groups are isomorphic? And that's a great question, and that's what most of this course is about. So most of our further discussions are to develop tools, ideas, concepts, machines to answer this question, when are two given groups isomorphic? How do we tell the difference between two groups abstractly? That's what abstract algebra in a lot is about. These are isomorphic. Now, what you're saying is right. If you can map generators to generators and relations to relations, I mean, there's something that can be said there. Certainly, we don't want to stay with the burden of drawing Cayley tables and making sure they have the same pattern. That's awful. And yet, it's better than making a case-wise defined function when you got 8 things. I don't know. I regret not saying this last year for the students, okay? There's a reason I'm telling you guys this. And I really have a lot of respect for Nicholson telling you that early in the book before he gets to the isomorphism section. He just makes an informal comment in section 2.2 that 2 groups are isomorphic if they're kind of the same, right? He doesn't actually come out and say what I said here. This is in a later section, right? But I think it's helpful to have the precise definition earlier. So I did. Now, so what's a subgroup? Don't want you to call me a liar. What's a subgroup? I mean, you can say whatever you want, but. So you guys remember what a subspace was in linear algebra, right? Subgroup, same song and dance. So H, subset of G, a group. We say H is a subgroup. Let me say that we're dealing with G comma star just to be precise. H is a subgroup of G star if star restricted to H cross H makes H a group. In words, if you take the operation of G and you restrict it to the subgroup, right? If that subset is then a group, we say it's a subgroup. And we write H less than or equal to G to denote that. Where am I? Example 9. So here's a family of subgroups. Here's a chain of them. The integers are an additive subgroup of the rational numbers, which are an additive subgroup of the real numbers, which can be viewed as an additive subgroup of the complex numbers. Let's get crazy, which can be viewed as an additive subgroup of the quaternions. Oh, the quaternions entered the scene. Yay! We'll come back to those. On the other hand, this is all additive. And example 10, same song and dance, but multiplicative. So just put a star. I should have just called this example 9 star. That would have been smarter. Too late. Multiplicative. These are subgroups. Each one's a subgroup of the other. Another nice example, which doesn't take a lot of thinking. The alternating group, A sub n, is a subgroup of Sn. We've argued that the set of even permutations, the composition of any 2 even permutations is again even permutation. Inverse of even permutation is an even permutation. The identity permutation is an even permutation. Put these things together, inherit the associativity from permutations. That gives us that the alternating group is itself a group with respect to the same operation, namely function composition as Sn. So that's another good example of a group, subgroup rather. Now, subgroup, the concept of subgroup gives us a way of generating all kinds of new examples. The principal tool in this conspiracy to generate new examples for you guys is the following theorem, which is basically the subgroup test, which I will state next time. And instead, I will just give you an example of the subgroup test theorem. Example 12, we can define SLNR to be A in GLN R such that the determinant of A is equal to 1. This, in fact, forms a subgroup of the example 1 I did today. Why? Because if we have A and B are in SLN R, then you can notice that the determinant of AB is the determinant of A, determinant of B also known as 1 times 1, which is 1 again. So therefore, AB is an SLNR. And also, you can easily prove the determinant of A inverse is the determinant of A inverse. Sorry, it seems like I said nothing. I actually said something. Be careful with the reciprocal notation. It is frowned upon to write 1 over 2 bar. Thou shalt write 2 inverse, or 2 bar inverse. Thou shalt not write 1 over 2 bar, for it shall make the Sprano unhappy. And so this is 1 over, well, this is 1 inverse, which of course is 1, right? And also we can, is the identity in this SLNR, the identity matrix has determinant 1, right? So that shows that it's non-empty. It has the identity matrix in it. It's closed under multiplication. It's closed under inverses. And this is basically what the subgroup test theorem says. If you can show it's closed under products and inverses, and if it's got 1 in there, it's a subgroup. This is called the special linear group. That's why the L. And again, what's R? Go back to example 1. Any of your favorite flavor choices. And we could add more on special days for people with certain names or something. I don't know. But. All right, with that, I should stop because we have important business to attend to.